Yes. Okay. Let's see if we can see your presentation. Yeah, perfect. Now it's working perfectly. So please go on.
I think you're muted.
Oh, Daohai, we cannot hear you. Can you check the microphone?
Yeah, sorry.
Yeah.
So hello, I am Daohai Li from Beijing Normal University, and I'd like to talk to you about how asteroids pollute the white dwarfs. And this is the work done together with Alexander Mastu and Melvin Davis, both from Lund University. So first I shall say a few words on the white dwarf metal accretion, and then I will show how we model the accretion of an asteroid onto a white dwarf. And that our modeling would consist of two parts. The first is tidal disruption, and the second being the long-term evolution of the fragments. And we will pay a special attention to whether a disk will form or not. So first, white dwarf metal accretion. So I guess most of you would know that so for about a quarter to half of the white dwarf, we see metal absorption lines. And here we have the calcium absorption line from a bunch of white dwarfs, and we can see the absorption line. So the point is that for a white dwarf, its gravity is extreme. So for example, compared to the sun, its mass is it's of the same order, but its radius would be 100 times smaller. This means that the surface gravity at a white dwarf would be 10,000 times that of our sun. As such, the heavy elements, I mean anything heavier than the main component of the white dwarf, which is the hydrogen or helium, those metal elements would sink very quickly. And on the right, we show the sinking timescale as a function of the white dwarf cooling age for the metal elements. And the red lines are for the hydrogen-dominated white dwarfs, and the blue line for the helium-dominated white dwarfs. So the point is, although this sinking timescale can vary from a few days to a few million years, they are all much smaller than the cooling age. This means that if we observe some metal in the white dwarf atmosphere, that kind of metal accretion must be ongoing. So how does the metal accretion occur? Because objects within a few AU would have been cleared out during the giant branch. So a model for white dwarf metal accretion is that in unstable planetary systems, small bodies can be scattered towards the white dwarf by planets. And we can use a 3-planet system example, and in this system there are 3 planets and a small body and a belt of small objects. And when the system evolves from the main sequence towards the giant branch, the central host would lose its mass, and this would cause the semi-axis of those objects to expand, and there would be increase in the interplanetary forcing simply because the central host loses its mass. And also there will be an increase in the mutual separation because their orbits expand, but the first factor would outweigh the second, such that the system can be unstable. So the planetary orbits can be excited, and then the planets can then reach the belt of small objects, and those objects can be scattered onto the white dwarf. Then when an asteroid is scattered close to a white dwarf, it may end up directly accreted by the white dwarf. This would mean that the pericenter of the asteroid has to be smaller than the physical radii of the physical radius of the white dwarf, which is about an Earth radius, or it can be tidally distributed, and this only requires its pericenter to be smaller than the Roche radius of the white dwarf, which is roughly solar radius. So apparently, an Earth radius is only 1% of the solar radius. This means that tidal disruption is much more likely. So here we come to our modeling. We want to model how a tidally disrupted is accreted by the white dwarf, and our model would consist of 2 steps. The first is the tidal disruption, which lasts a few orbits, and then we will also consider the long-term evolution of the fragments. We will include the planet fragment interaction, the fragment interaction, and we will consider the white dwarf radiation. So the first step is the tidal disruption. So in the solar system, kilometer-sized asteroids are mostly rubber piles, and those are held together by gravity only, so there's no cohesion. And this comes from 2 lines of evidence. The first is the rotation limit. So on the right, we show the rotation period of the asteroids as a function of their diameter. So we can see that for asteroids of the size of a few kilometers, there is an lower limit on the spin period. And this can be understood in the following way. So if we have something on the surface of the asteroids, there will be a critical rotation frequency such that the centrifugal force is equal to the gravity of the gravitational force from the asteroids. And so there is a critical rotation frequency, which translates to a critical rotation period. And it can be expressed in this way. If we take that, the density of an asteroid would be, let's say, something like 2 grams per centimeter cubic, we get that this critical period is 2 hours or so. So this is why we get this limit. And also for asteroids, because their collisional velocities are typically of a few kilometers per second, so these collisions can be highly destructive. As a result, if an asteroid is a few kilometers in size, their collisional lifetime would be much shorter than the age of the solar system. So if we have kilometer-sized asteroids, it's not likely that it is monolithic. So we model an asteroid as a rubber pile of thousands of particles. And here is an example of a rubber pile asteroids. And we consider the gravitational interactions and the inelastic collisions between the particles. So we would like to show you an example of tidal disruption. So in our model, we have a white dwarf, we have a rubber pile asteroids, and we assume that the bulk density of the asteroid is 2 grams per cubic centimeter. And we have 8,000 of particles for the asteroids. the percent distance is 0.004 AU, which is inside the Roche limit. And we run the system for 50 days. And on the right, we have the asteroids. So each point is a constituent particle of the asteroid. And here in the figure title, this D is the distance between the center of mass of the asteroid to the white dwarf. So we run the system. So when the asteroid is far away from the white dwarf, so basically it's not deforming. And this arrow points to the direction of the white dwarf. So after the pericentric passage, this asteroid is basically shredded into its constituent particles, and those particles may accrete because of their self-gravity. Now, the picture we have is that after the tidal disruption, we would get a stream of tidal fragments. So now we come to the long-term evolution of the tidal fragments. So though not explicitly modeled in our simulations, we assume that it is a planet that scatters the asteroids close to the white dwarf in the first place. Therefore, when the asteroid is shredded into fragments, the planet will continue to interact with the fragments. So in this sense, we will consider the planet fragment interaction, and also the white dwarf is in some sense also luminous. So we will consider the white dwarf radiation force, and we will consider the mutual fragment interactions. So first, planetary scattering. So in our example simulation model, we have white dwarf, we have the tidal fragments from our previous tidal disruption simulations, and we have Neptunian mass planets on an eccentric orbit. And here we only consider the gravitational interactions. And we run the system for 10 million years. The result. So some of the fragments would hit the white dwarf, and some others would be ejected out of the system. So on the right, we show the cumulative fraction of the fragments that hit the white dwarf or be ejected. So we see that the ejection is always not important. And for hitting the white dwarf, we have a initial surge within a few thousands of years. And after that, we have a long tail. And overall, a few tens of % of the fragments would hit the white dwarf. And then we would like to pay attention also to the orbits of the survivors. So here we show the fragments pericenter distance and their inclination. So at time 0, that is just after the disruption, all fragments have exactly the same orbits. So they have the same, so their mutual inclination is basically 0. But at 10 to the 5 years, as the blue point shows, their orbits are very much dispersed. So the optical dispersing timescale is 10 to the 4 years. Next, we come to the white dwarf radiation force. So we have white dwarf and we have fragment. So, and here we only consider the immediate absorption and the reflection of the white dwarf radiation. And because this kind of force is highly stellar-centric distance dependent, so we can think of such interaction as a kick at the pericenter, and this would cause the epicenter of the fragment to shrink. So it would be like this. Yeah. So here, when we numerically model this process, we have the white dwarf, and its luminosity is a % of the current solar luminosity. And we have the tidal fragments from previous simulations, and we just evenly distribute the fragment size between 1 millimeter and 1 kilometer. And we have the planet, and we have the, let's see, the white dwarf radiation force. And we again follow this system for 10 million years. Result. So fate. We have seen that ejection is very minor. So here we only consider heating the white dwarf surface versus orbital shrinkage, and this later comes from the effect of PR drag. And we have said that orbital shrinkage is highly physical size dependent. So we show this figure here. The x is the radius of the fragment, and the red points means that the fragment is orbitally shrunk, and the black point means that the fragment is accreted by the white dwarf, and the y is just the time of the event. So we see that for orbital shrinkage, we must, as the fragment must be smaller than 0.1 meter or so, and it's only efficient before, let's say, 10 to the 4 years. But for accretion, it can last for a long time, and it works for large fragments. Finally, we have the fragments' mutual interactions, which is collisions in this case. So because the let's say the velocity dispersion between the fragments is so high, so we can safely ignore the gravitational interactions, but collisions may be important. So here we estimate the collision probability between two objects following Tesla, and the probability can be expressed in this way. So this sigma is just the physical collision cross-section, and this p is the chance that we have two objects at a radius of r and a latitude of beta, and this v collision is the collision velocity. And it turns out that this probability is highly dependent on the inclination of the objects. And here we have the relative collisional probability as a function of the object's inclination. So we see that, for example, at 0.01 degree, the collisional probability is about, let's say, 100 times of that when the fragments have an inclination of 1 degree. Yeah. So now we apply the previous collisional probability calculation to the real fragments from our tidal disruption simulations, and we integrate that over time. So we get the cumulative collision probability between a random pair of objects. And what we see here is that, so basically this is a steep function before a few times 10 to the 4 years, and after that this is a straight line. And because this is a cumulative probability, this means that collision are only possible in the first few 10 to the 4 years after the tidal disruption. And we consider that the collision probability scales with n square r square, which where n square is just a number of fragments. And we see that here the absolute the absolute collision probability is, let's say, of the order of 10 to the minus 10. So if we want this to be near unity, we would need 10 to the 5 1 kilometer sized fragments. This means that for the mutual collisions to be important, the asteroid has to be as large as 100 kilometers or so. This means that collisions are only significant for large asteroids. And and because their relative velocities are so high, they
Yep, 2 minutes more.
Yeah, thanks. Yeah, I'm nearing. Yeah, and because the velocity dispersion is so high, those collisions would be super catastrophic. So from those collisions, we would have from tidal fragments into collisional fragments, and those collisional fragments may mutually collide further. And because when we have these mutual fragments, those are much smaller than the tidal fragments, we have a much increased surface area to mass ratio. So mutual collisions, once initiated, will proceed in a runaway manner. Now we see the synergy between collision and white dwarf radiation forces. So when we have collisions, we would get smaller fragments. And here the black line means the direct result. And PR drag would lead to smaller orbits. And yeah, because of when the fragment size gets smaller, we would get faster mutual collisions because of the increased surface area to mass ratio. And here the blue lines means to enhance. And for the same reason, we would have a stronger PR drag. And when we have small orbits, then the time scale of the things then the time scale for the mutual collisions would be also smaller, and so is the time scale for PR drag. This means that this means that we would end up with a circum-white dwarf dust disk. But we remember that we have a constraint imposed by the planet scattering that is 10 to the 4 years. So if the synergy between collision and PR drag can happen, that must happen within 10 to the 4 years. So we now reach our overall picture. So if we have large asteroids that is 100 kilometers or 10 kilometers, depending on the composition of the asteroids, we would have a large number of tidal fragments. And this means that collisions and PR drag would be important, and we would have a dust disk. Otherwise, if the asteroid is small, planet scattering would dominate, and there is no disk. So to summarize, not all accretion of asteroidal material onto the white dwarf takes place through a disk, and the occurrence rate of disks depends on the asteroid properties. And for the full results, you can check this work. And I guess that's what I have to say. Thank you.
So thank you very much for your presentation. I was muting myself. So we have already a question by Dimitri. Do you want to proceed and ask the question, please?
Sure. Hi, Daohai. That was very nice review. Thanks very much. I was curious if the initial asteroid that you used was actually aspherical. Do you think the results would change much? Do you have some intuition as to where those fragments might actually, how they would deviate from the results that you got?
Yeah, we have not thought about the let's say the non-spherical shape of the asteroid, and I would intuitively guess if we have a non-spherical asteroid, let's see, the orbital dispersion of the fragments might be larger, and this may lead to a somewhat slower collisional process. But then this would mean that in order to have, let's say, fast collisions, we would need larger asteroid. But that's my guess.
Thanks. I know it's not an easy question, but I saw that your probability plot was a function of inclination. So maybe
Yes,
that parameter would change a bit depending on what the dispersion of those fragments are.
Yeah.
Oh, we have another question in the chat that is asking you: do your conclusions depend on the size distribution of the fragments?
Yes, that's very true. So when we see, so here we see that large asteroid would lead to the formation of a disk, and here, if the asteroid is monolithic, the typical, let's say, the typical tidal fragment size would be 1 kilometer or so. So in this case, the surface area to mass ratio is small, so we need a really large asteroid. On the other hand, if we have a rubber pile asteroid, and because the particles in those rubber pile asteroid would have sizes, let's say, in the range very roughly between a millimeter to a few tens of meters, so we would have a relatively larger surface area to mass ratio. So here, the large asteroids only need to 10 kilometers or so for the collisions to be important.
Okay, we have another question in the chat from Antoine Tullier. I don't know how to pronounce his surname, but he asked, thanks, but first he congratulates you for the talk, and also ask for large bodies of about 100 kilometers, what they would be differentiated. Do you expect a lot of variation in this scenario?
Perhaps, because I would assume that for differentiated objects, the core would have a higher density and also perhaps higher, let's say, a material strength. This would mean that you might get, let's say, larger fragments at the same pericentric distance, and this would change the surface area to mass ratio, and I guess that may change our definition of large asteroids.
Okay, now we have a question by Tom Marsh. I think we still have at least one. This one more question is, you seem to have a direct impact or rejection. Either direct impact or rejection. What about evaporation or unclosed passage by the white dwarf? So I was going to ask a similar question. What about the sublimation of the material? Would you expect some impact from that?
Yes, and indeed here we only consider direct impact onto the white dwarf or ejection. And as we see, the ejection is probably quite minor. And when we include evaporation,
Okay, I think tough question, I guess. And I think we can move to the breakout room. So I need to figure out how to figure out how to do it. I think so. I will create 2 breakout rooms. If you and Daohai can join you in the first room, and then Daohai in the second room, that would be perfect. I know that you are in a hurry, Daichi, so at least maybe you can stay for a couple of minutes and then just go.
Yeah, I can stay there for like 20 minutes or so.
Yeah.